Let's continue talking about the synchronous generators. We briefly introduced two types of the generators based on the rotors, cylindrical rotor generators and round rotor generators. Each synchronous generator will have a number of windings we need to model, including the windings on the stators, which are phase A, phase B, and phase C. And on the rotors, we need to model the field winding, and also there could be a damper windings. So let's go to the detailed modeling for generator. So we use cylindrical rotor as one example to talk about the modeling, and later we can add some additional consideration on the round rotor. So you can tell, so in the figure, if you see the cross-sectional area of the generator, the outside, the ring outside is about the stator, and the windings are embedded into the stators. So for instance, if you see find the phase A, B, and C. So this is phase A. So I put a little circle with a dot in it, which indicate the current coming outside of the screen. And on the other side, you see the A prime with a little X at the center indicating the current going to the screen. So the phase A doesn't change. It stays inside of the stator. Stator doesn't move. So because we assume the rotor revolves counterclockwise. So if the rotor face the axis of the phase A and after another 120 degree, it will be facing the phase B. So B will be here, and this is B prime, and the C is here, and this is C prime. So those three windings will stay there. And we need to model those three windings. Then for the rotor is you see which is revolving inside of stator. So we have to give the rotor one axis. For the cylindrical rotor generator, the longer the longer shape, which has a smaller air gap, that one is defined to be the d-axis, so direct axis, which is the same direction of the magnetic field. And another axis, which is orthogonal to the d-axis, is called a quadrature axis. So this is a d, and this is q, or quadrature axis. So in today's literature, usually the q-axis or quadrature axis is defined to be a 90-degree leading d. But if you find any old textbook or old papers, some paper used to have a q lagging d, but the IEEE standard has require defining q to be leading. So on the rotor, we have a number of windings to model. First, the most important one will be the field winding. The field winding will have, so if we assume this is the direction of a magnetic field, right? This is N. The other side is S. So based on the Ampere's law, right? So you need to have to generate this magnetic field, you need to have current coming out from this side and going from the other side to give you that magnetic field. So this will be the F field winding with F and F prime. We may also model another winding, which is the damper winding in the d-axis. So we draw this capital D next to capital F, which is in parallel with the field winding, and the D prime is here. So those are all we need for cylindrical rotor generator. So we have, and also we need to have the damper winding in the Q axis. But for round rotor generators, we want to make the number of windings to be symmetric between D and Q. So we add another damper winding, or the second damper winding also in the Q axis. Because right now for the cylindrical rotor generator, we have 2 windings in D and 1 winding in Q. So we add the second damper winding in Q. So now each axis we have 2 windings. We have the same number of windings. So later when we show the structure or equipment circuit of cylinder generators, you can add any number of damper winding leg. So for instance, if you have a one field winding for cylindrical rotor generator, you don't have to make the windings on D and Q to be equal. So you can have 1 damper winding plus in D and 1 damper winding in Q. You can also have 2 damper winding in D and 2 damper winding in Q, or 3 damper winding in D and 3 damper winding in Q. So the total number of winding, they don't have to be equal. But for round rotor generator, usually we expect a same number of windings. So which means for round rotor generator, if you already have 1 field winding in D, okay. And also another damper winding in D. So you will add 2 damper winding in Q. So such as you have 2 rotor winding in D and 2 rotor winding in Q. So for cylindrical rotor generator, for this case, we need to model at least 6 windings, 3 plus 3. But for round rotor generator, we need to model 3 plus 4, 7 windings. Next, we want to model the angle, determine the position of the rotor. So if we make this axis, this is the axis of A winding, because winding A is here, right? So if you think about the winding, it's actually a core horizontal, and the axis will be vertical. So if you want to describe the position of rotor relative to stator, and we use the axis of A as a reference. So this is the D axis. The separation is theta. Theta will be a variable indicating position of the rotor. So say when the rotor is revolving, theta will change, actually increase monotonically with time, because the rotor is always revolving in the same direction, so it never go opposite. So theta will increase with time, so it's not a constant value. Okay, but then that's not very convenient, because when we have many generators to model, we don't really know which direction each winding A is facing inside of each generator. So it will be more convenient for the entire system. We define a common reference axis. So this common reference axis could be pointing to any direction. It doesn't really matter. For this generator, by default, we can just assume this common reference is in parallel with the axis of A at time 0. But what is time 0? It's just any time you start counting. But this reference frame is not stationary. It's changing together with rotor at the speed of the rotor speed. Okay. So let me repeat this again. So at time 0, so assume the reference of the DS is in parallel with A when the rotor is not revolving. But once the rotor start revolving, gradually increase to the speed omega r, and this frame will change together with the rotor. But the axis of winding A doesn't change. So you can see the separation between this reference frame and the axis of A will increase with time. Why do we need to define this reference frame? Because we assume all generators operate at around 60 Hertz, very closely at the same speed. So we can assume a common reference, which is operate exactly at 60 Hertz, right? Even some generator faster, some generator slower. So the angle separation from that common reference can be controlled. So if they stay within a limit, we will see all the generators are in synchronism. If any generator has angle separation growing until it become uncontrolled from the reference frame, then we'll see that generator become out of step. So it's very important to define such revolving reference frame at a common speed, so we can estimate whether each generator can become stable. Okay. So next step, we need to define the position of the rotor relative to this revolving reference frame. So and we introduce another angle delta. Delta is defined to be the angle separation for the Q axis from the reference frame. Okay, theta is the actual position. So if you're able to measure where the rotor is, if you can measure, or maybe you put a camera inside of the generator, you just measure the position of rotor, that's theta. That's the physical actual location of rotor, right? And reference frame is a fictitious frame revolving at singular speed, or maybe average speed of all generator of the system. And the delta is the QS is relative to that common reference. So delta will be very useful. Delta can be estimated or measured using just voltage or current, but it's very hard to know anything about theta, and theta is not useful at all. Okay, so delta is defined to be the displacement of Q axis from the rotating reference frame. Because we let Q be the we define the position of Q as delta, then there will be this simple relationship. So if we know theta, we subtract the angle increase by time, and then we plus another 90 degrees. 90 degrees because Q is leading D by 90 degrees. Then this will be delta. Okay, so when T is 0, if T is 0, the theta is 0 and omega T is 0. So those two items will be 0, right? Delta at the beginning, time 0 is 90 degrees. So when T increase, delta will increase. So why do we define Q axis to as the delta, not D axis? Because later we'll see if we define Q as the axis as the delta, so the any phasors, voltage or current in Q axis will be in the imaginary axis. In the D axis will be in the real axis. So it's more convenient to introduce complex numbers, right? Because the imaginary axis leading the real axis by 90 degrees. So if you remember the 421, we introduced a complex number to model voltage, current, we introduced the concept of phasor, such as each voltage phasor, current phasor can be treated as a complex number. So you have real part, imaginary part. So later we'll draw all the quantities, voltage, phasor, current into also the complex plane. So if we define the delta to be the position of the Q axis, we'll make the imaginary axis to be Q and the real axis to be D, right? Q is leading D by 90 degrees. So you understand why it's more convenient to define Q to be leading D, not lagging D. If it's lagging D, so all the quantities in the Q axis will have to have a negative sign, but it's not very convenient. Okay, so yeah, we'll come back to this phasor representation later. So now just summarize, the theta is the actual position, and there's a fictitious reference frame revolving at singular speed, and the delta is the Q axis relative to that reference frame. So if all the rotors of the entire power system revolving at the exactly same speed, so the delta never change. They will keep constant. Okay, so next we want to start listing some equations to model the quantities about the generator, including voltage, current, or flux linkages. We use a cylindrical rotor generator as one example. Because we start modeling for the generator. So let me explain the goal or the objective of modeling. So when we see any statement about we are doing the modeling for something, so what is the modeling really doing, or what is the goal? The modeling is trying to find. So if we have the physical equipment, right? So our goal is to find maybe a number of equations. Equation will have variables and also parameters. The number of variables depend on how large space or how complex you want to consider this equipment. So the final goal is to find a set of constant parameters. We want to make the constant parameter to be, the number is to be minimized. Okay, so for instance, if you have a transformer, you can model, if you still remember the principle of transformer, you need to model the ratio, right? The ratio of turns. And also you may model some voltage, current, or there could be maybe leakage flux. So there are a number of things you need to model. If our target is to find the most accurate model, we don't want to ignore anything, or we want to keep all the features of this equipment, maybe you can find a model. Finally, the model have only 3 parameters. For the 3 parameter, you just pass the model to the engineer who can help you to do the field testing to estimate those 3 parameters. Once you know the 3 parameters, you can use the parameter for your calculation. So that's very convenient. But if there's another engineer who just have another model, and the model doesn't have 3 parameters, but instead of 3, you have 5 parameters. So that model is not better than your model. If both models gave exactly the same result, so the more parameter, the less efficiency for the model. So our goal is to give a desired accuracy. So you can define the accuracy, and then we find the minimal set of parameter. Okay. So later you will see how we can reduce the number of parameter without sacrificing any accuracy of the system. So we have considered like 6 windings for cylindrical rotor generator, right? 3 plus 3. So we need to model each winding as an individual circuit. And also we need to model the coupling between any 2 windings, if they do have coupling. If they have no coupling, we ignore that coupling. So this one reminds you of something like a transformer, right? For transformer, if you have a 2 winding transformer, each winding will have circuit. And so 2 windings, they don't have physical connection, but they couple through electromagnetic field. So you need to introduce a parameter which is mutual inductance to model how the current on one winding can affect the other one. So we borrow the same idea. So now we have a 3 stator winding, 3 rotor winding. So that may remind you of something like a 3 winding transformer. Okay, or 3-phase transformer. So let's draw the circuit. Okay, on left-hand side, we have a 3 individual circuit. Okay, so each circuit model 1 winding, one of the 3 rotor winding. So we intentionally to draw 2 winding. So when we talk about winding, we really talk about this inductance. So we intentionally draw 2 inductances vertically and another one horizontally. So your vertical label means that's a d-axis. So the first 2 will be the d-axis. And maybe I need to draw the lowercase. Yeah, this is d-axis, and the third one is actually q-axis. So I have 2 one in the d-axis, 1 in the q-axis. So those 3 are not connected, right? They're just individual circuit. And on the stator side, we have 3 winding, but they physically connected at the neutral point and to the ground. So this is just to flow the short circuit current. If you have any imbalance or any short circuit on any line of the system. So those 3 stator winding will go to the power system, right? They will send energy to the three-phase power system. So it will be connected to the rest of the system, of the load. And the nice thing is you take a look at for each winding, if we treat it as circuit, we'll have a source. We have a resistance. A resistance just indicate each one is not perfect, not a superconducting material, so it will have some resistance. And the industance is actually the winding itself. For the three rotor winding, we have definitely this is the source generating the field current. So it will be a DC source to generate the field winding current. But for the other two circuits, which are the damper winding, they don't have internal source under steady state condition. So when the system is the rotor revolving at constant speed, the damper winding, they don't need to be affected. They don't need to do anything. But if the rotor is shaking or oscillating, so there will be current induced inside of the damper winding. So we put 0 for the normal condition, but under the abnormal condition, those voltage will be non-zero. Okay. They also have damper. They have a resistance. For damper winding, the resistance need to be really large because we want to utilize their resistance, right, to change oscillator energy to heat. But for field winding, we will expect the resistance to be very small. So those are very reasonable assumptions based on the actual design of a cylinder generators. Later, when we go to the circuit, we'll utilize those assumptions. Like a damper winding resistance is much bigger than the field winding resistance. Okay, so those are the three winding on the rotor. And another assumption we make is we make the direction of a current and flux in the same direction because windings on the rotor circuit are actually treated as loads, not source. Because you have the DC source, which is the which is EF, ED, or EQ to generate the current, and current will flow through the winding, the inductance to have voltage drop. So on the rotor side, the inductance is treated as a load, but on the stator side, inductance is treated as source because the windings are coupled, so the voltage will be induced due to the stator winding. Okay, so you can see so when we have the direction of the flux linkage pointing to this direction, and the current is opposite. So current is opposite to the direction of the flux linkage because the voltage on the stator side is induced due to the change of the current. So based on that convention, we make a current be opposite to the flux linkage. So next, we're ready to write down some circuit equation. That was, yes, okay. So on the rotor side, if we make we use this field winding circuit as one example. On left-hand side, we have a source voltage. Right-hand side, we have voltage drop on the resistance, and also voltage drop on the inductance. So this is the single equation. Definitely, if you write the equation for the damper one, that's exactly same structure of equation. You just change the subscript from F to D or to Q. That's exactly same equation, same form. On the stator side, the source is actually the winding itself, right? It's change of the flux linkage in the winding. So that will induce voltage. So that voltage will become voltage drop on the resistance, and also this voltage will be drop on the load on the outside of this generator. Okay, so we have the flux linkage. We have voltage equations on both type of windings. But sometimes we want to make the two voltage equation to have the same structure. Then we can put into the one group. So we just do a little change. We move voltage to the left-hand side, everything else on the right-hand side. Okay, so you see for the stator winding, you have a negative sign in front of this product of R and I. So that's the only difference from the rotor winding. So we have 6 winding. Later we'll have 6 voltage equations. All the equation will be structured in such form. On the left-hand side will be the voltage, instantaneous voltage. Right-hand side, the first item is voltage drop on the resistance, and the second is voltage on the inductance. And if that winding is stator winding, you will see a negative sign, okay, in front of this Ri. Okay. Next, we want to write the flux linkage equation. All the equation will have this form. The left-hand side will be the flux, total flux linkage in that winding, and the right-hand side will be the summation of many terms. So each term basically is 6 terms because we have 6 windings, right? Each one will be the product of the inductance and the current. So if we talk about the flux linkage of F winding, so we are going to consider there will be one item which is the current and flux linkage of this winding itself. That's one item, and the second is the current and the inductance of this winding itself. The second will be this current multiplied by a mutual inductance between F and D. And then this IQ multiplied by the inductance between F and D. And also there will be a coupling to all the 3 stator winding. So such product will have, in front will have either positive sign or negative sign. So for negative sign, that will be the coupling with the stator winding, because for stator winding, we define the current to be opposite to the flux linkage. Similarly, for the each flux linkage on the stator, it also will be the sum of the 6 items. So each item is product of inductance and current. So for the items, the coupling with the stator winding, there will be a negative sign. All right, so we have totally we have a 6 voltage equation, 6 flux linkage equation. We have a 12 equation now. Let's categorize, because the key here is to find the value of all the inductances, because the resistances can be measured or can be estimated. So if we know all the L's, all the inductances will have the first model. So there are several types of inductance. The first one is called rotor self inductances. So there will be a 3 item. So which will be LFF, LQQ, FDD. So that means the self inductance on each rotor winding itself. And the next one is a rotor mutual inductances. So it will be LFD, DQ, and FQ. Okay, so those are the coupling between the 2 rotor windings. The second group will be inductance only about stator. So it could be a self-inductance, so it will be LAA, LBB, and LCC. So that's only the inductance involving just a single winding on the stator side. And then the mutual inductances will be LAB, LBC, and LAC. So those are the inductances involving 2 windings on the stator side. Finally, we'll have mutual inductances between stator and rotor. So those L will have the first subscript from the stator and the second subscript from rotor. So it'll be one lowercase letter and one capital case letter. Okay, so now we can put all the equation together. We have a 6 voltage equation. So we have this vector will have all the instantaneous voltages from EA, EB, EC, and EF. For the ED and the EQ, which are the instantaneous voltage in damper winding, so they will be 0 for most of time, and become non-zero if the rotor is oscillating. Okay, so it'll be an induced voltage inside of damper winding. And then we make the first item on the right-hand side involving the product of resistance and current we can make all the resistances put into one square matrix, which is diagonal. And the current is also one vector, right? So you see on the current on the stator will have negative sign. And the last item will be the derivative of the flux linkage. So this will be the set of voltage equations. And you can write all the equation in this matrix form. You can define the vector of the voltage, the 3-element vector as the EABC, and the voltage vector on the rotor as EFDQ. Any question so far? All right. So next, we just simply put all the flux linkage equation here. Left-hand side is a vector of all the flux linkages, right? ABC, FDQ. Right-hand side is the current vector. So we still have like negative sign for stator and positive sign for rotor. And then this matrix will be our goal to estimate, because this includes all the parameters we need to determine with 6 by 6 elements. Each one will represent either self-inductance, which is on the diagonal, or mutual inductance on off-diagonal. All right, so we can also write this one into this matrix form. So next step will be finding each L. So SY depends on which winding with which winding. So SY can be the same or be different. Okay, everybody follows. Let's move forward. All right, so let's figure out how to determine each LSY for this matrix. So we'll introduce this analogy, which is like transformer, or maybe just simply just two coils facing each other, and in between there's a magnetic field revolving. It can be stationary or revolving. We can use the same system to study any element in this matrix, okay, to determine how we can find the expression on that L, either it's constant or changing. Okay, so each winding can be any one from the 6, from A, B, C, or capital F, capital D, capital Q. So we know if we put two windings or two coils in this way and have a revolving magnetic field, the mutual inductance between the two windings, if we call it LSY, so that one is equal to NX multiplied by NY multiplied by PSY. Okay, so NX is actually the total number of turns on the winding X, and NY is the number of turns on the winding Y. And PSY is actually the permeance, which is like a conductance for resistor. And we know because of symmetry, if we calculate, if we define, because this formula doesn't tell the direction of SY, right? So because if we calculate LYX, that's same formula. So then we will conclude there's a symmetry regarding this inductance matrix, which means any element like LFA will be equal to LAF. So this matrix has to be a symmetric matrix. So we only just need to determine the top triangle element, right? If we know everything in the triangle, we also know the other side of the matrix. Next, we want to just apply this small system to determine value of each L. Another thing we need to consider, okay, so for transformer, if we use this one system to represent transformer, so windings, they're tightly coupled, and also the magnetic field doesn't really change. But if we use this system for generator, at least one part of the 3 elements need to change. Okay, So whether you have, okay, if this winding represents the stator winding, and this winding the left winding represents the rotor winding, which means the winding X and this rotor together will revolve. So they will move together. Okay, that's one case. If both windings represent a stator winding, they don't move. The rotor itself will remove, right? Will rotate. That's the second scenario. The third scenario is if both windings are rotor winding, so they together will revolve. So you either have two elements or one element, all the three elements revolving together. Okay, so that exactly match the three scenario in this matrix. So we'll show that one shortly. So we can utilize this product NS multiplied by NY as effective coupling. What effective coupling means is we treat each NX or NY as a phasor because the winding can revolve. So when the two axes of the two windings are in parallel, so their effective coupling will be the maximum, so which is equal to the product of their magnitudes. But if one winding turns by 90 degrees, so even the actual number of turns of each winding never change, but the effective coupling becomes 0. So we can, which means we can treat each N as a phasor with angle. So when the angle is 0, they will like inner product of two phasors to have the maximum value. But when they become orthogonal, so that effective coupling will become 0. So we can use this one to model the relative positions. P, as I said, is just permeance. What determines the P? Actually, P depends on the distance, air gap, between the magnet and the winding. So if the air gap is 0, the permeance will be largest. If the air gap increases, the permeance will decrease. So why does the permeance change? Because if the rotor changes to this position, so the air gap becomes bigger, right? The permeance will decrease. So when the rotor revolves at similar speed, you can imagine that the permeance will also change as a periodic function. All right, so both the product of N and the permeance can change periodically, but at their different frequencies. I will explain in a minute. Okay, so let's first take a look at the rotor inductances. Let's take a look at everything in this block, which is this block matrix LRR. They are simply just all constant. Why? Because this is exactly the case for the two windings and the rotor itself together revolve. Okay. So there's nothing to change. Okay, so both the effective coupling is constant because the two stator rotor winding they stay at the same position, just change together, and also they change with the magnet. So this permeance also doesn't change. So they're all constant. So we can give each element a constant value, and we can even know some of the value must be 0. For instance, this one. This one is a mutual inductance between F and Q. F and Q are two windings orthogonal to each other. Okay, so their effective coupling must be 0. So this one has to be 0. So for any element involving two windings which are orthogonal to each other, that has to be 0. And the other could be non-zero. We'll determine those values later. Second tab, which is in the green box. So this indicates all the inductances involving only stator winding, not rotor winding. So for this case, the two winding will not change. The two winding will not change. Only the rotor will revolve, which is like this one. Okay, so when the magnet is revolving, the air gap will change periodically. So as period of 180 degree. Why is 180 degree? Because if the n change to here, so this one become n, and the other side become s, the R gap will become smallest again. So after every 180 degree, the permeance will reach the maximum value. So now the 360 degree. So as I said, the permeance only depend on the air gap. It doesn't tell the direction of the magnetic field. So every 180 degree of the rotor, the permeance will reach the maximum value. So we can reasonably assume the permeance will change as a periodic function at 180 degree. So we can use a cosine 2 theta plus certain phase to indicate, to model this periodic function. So if we assume the change is a sinusoidal shape, so this function will have 180 degrees as period. So for anything in this green box, they all have the same form. They may have constant term plus some periodic term. Periodic term will have 180 degree as the period. The last one in the gray box, there are in the gray box. So that is that involve all the inductances involving one stator and one rotor winding. So that for that case, the magnet will revolve together with one of the two winding, so which is like this one. So only one winding is revolving the other, but the magnet and the other winding will stay together. So for this case, that L will change as a periodic function of a 360 degree, right? Because after the other winding finish one cycle, one circle, so it will go back to the same value for the inductance. So we can assume those inductance will be this periodic function. And also you see, you see this animation. So when winding is revolving relative to the magnet and the other winding, the R gap doesn't really change. Doesn't really change too much. Okay, so next we just summarize. For the orange box, which is very simple, all constant. There's nothing to plot. Basically, all constant value. But for the green and the gray boxes, so element there will be a function of a theta. And for the green box elements, which involve the windings both from stator, so they will have period of 180 degree. For the gray box inductances, they involve one from stator, one from rotor, so that will be 360 degree. And each one will have certain phase. We don't know. That depends on what is the initial position. But right now, we assume the time zero means the D axis in the same direction as the Q axis. Then we can determine the phase. So if I assume at time zero, so D and A is actually in the same direction, so we can determine the phase. So the first group plot actually draw the inductances, anything, the self-inductances of the stator winding. So you can see the period is 180 degrees pi. By 2 pi, they finish 2 periods. And because we use the winding A as a reference, so we'll start from peak value. Then the second column is actually the mutual inductances will involve 2 different windings from the stator. And you can see the plot actually negative on the negative side. And the third column is the stator rotor inductances. So their period is actually 2 pi. So if we give their expression, so ILAA will have a constant part. We call it, we just use the capital LS to indicate this constant value. They will have a magnitude on the oscillatory part, and the phase is 0. 0 is just because we use a 1A as a reference, right? There's a phase 0. If you assume there's a phase. Then the LBB will have at 120 degree, and the LCC at a positive 120 degree or negative 240 degree. Typically, this constant part is much bigger than the oscillatory part. So such as the indulgence of LAA, LBB, or LCC will be always positive. It will be above the real axis. For the stator mutual indulgences, because that is about the indulgence involving a two winding separated by 120 degree. So their projection always opposite so their indulgence will be always negative, right? So it will be under the axis. So Quinter's book actually explains why this center value is roughly half of the constant part of the first column, but you don't have to remember that. The third column will be very simple. It just if we use LAF as one example, it basically just some magnitude and multiplied by just cosine theta. Okay, and LBF we just you add a negative 120 degree, and CF we just add positive 120 degree. So I say actually I didn't include all the details derivation of each formula, which are not required for this course. But for the 522 student, I suggest you watch this recording. That give you detailed proof of every single formula. But here I just quickly explain, right? I just quickly explain the form of each formula and how the phase can be determined, right? Quickly, but those are not required for 422. Let's summarize the model. So we derived the flux linkage equations, which include 6 equations to determine the flux linkage determined by the self mutual indulgences and with current. And first we need to identify the values of this indulgence matrix. Okay, so we can split it into 4 blocks, and because it's a symmetric, so we only need to determine the LSS, LSR, and LR. For the LSS, from the previous slides, we can put into this matrix. LSR will be this one, okay, and the LR will be all constants. So LSS will have a second order harmonic, right? So you see 2 theta for each item. And for SSR, that's a first harmonic. You only see theta without 2. And for LR, that's all constant. So we finished the first model for the signal generator, right? We have a 6 voltage equations and 6 flux equations, and we also for the parameters we gave an accurate expression. But unfortunately, this is not a good model. Remember I mentioned at the beginning. So our target is to find the minimal side of a constant parameter. And the parameter will be those indulgences. So at the end of this exercise, we did find a lot of parameters, but most of parameters are not constant. So this is not good model. Our next step is to find how to make those parameters be constant. And then we can figure out how we can reduce the number of parameters without sacrificing any accuracy. Okay, so yeah, we'll continue on next Monday.